form up the first one, you have x to the fourth, so you take 4 divided by 2, you get x squared. Y to the fifth is kind of like y to the fourth and y. So you get y squared on the outside and a square root of y stays behind. And then a to the seventh and c to the ninth, because they're both odd, you're going to have one left behind no matter what. So that a and c are going to stay in. And then a to the sixth becomes a cubed. B to the sixth starts even, but when you divide that by 2, you get 3, which is odd, so B needs absolute values. And then C to the 8th becomes C to the 4th. Okay, 24. The perfect square that goes into 24 is 4, and then 6. So the square root of 4 becomes 2. The 6 is going to stay inside. M to the 11 is odd, so you're going to have an M inside. So 10 divided by 2 is 5, so the 5 comes outside. 8 divided by 2 is 4. 4 is even, so no absolute values needed. And then you have the square root of R. Well, R has no pairs, so R stays inside also. So you have 2 M5 N4 square root 6 MR. Now, with something like the square root of 500 over 5, even though it's 2 separate square roots, you can think of that as one square root. So that's equivalent to 500 over 5. So you can take that 500 and divide it by 5, giving you the square root of 100, which is 10. So a division square root can be broken up into one divisor. You can also think of that as like 5 times 100, and that would give you square root of 5 over square root 5, which is 1. I don't know. I can't remember.
It's low rental children.
No, that was about us. Like everybody always tries to take gas because like what feels there, and like
Ghosts?
They're Jenna. That's just the turtle.
I think it's just turtle.
Alright, so we are going to be adding, subtracting, multiplying, and dividing radicals today. And adding and subtracting 2 radicals has a special little bit that goes with them. In order to add and subtract 2 radicals together, they must be what we call like radicals. So what that means is what's under the square root must match. So like you can't add the square root of 3 to the square root of 2 because they're not like radicals. But you can add a square root of 6 to a square root of 6. So like radicals must have the same index. So for now our indexes are all square roots. And then they must have the same radicand terms. So the radicand, if you recall, is what's under the radical. So we have 2 square roots of 3 plus 5 square roots of 3. These are considered like radicals, bless you, because what's under the radicand is the same. So the radicands are the same, therefore they are like radicals. So what you do is you add the outside numbers together. So 2 plus 5, you have 7 square roots of 3. And number 2, you have 1 square root of 2 plus 12 square roots of 2. So again, these are like because they both have root 2. So you get 13 square roots of 2. And number 3, our initial thought is, oh, these aren't like. Because you have a 72, a 32, and an 18. So then what we've been doing previously comes into play. So in order to determine if radicals are like, we must simplify them completely. So you're going to simplify 72. You're going to treat that like the square root of 36 and the square root of 2. And then you're going to say that the square root of 72 is equal to 6 square roots of 2. And then you're going to say that the square root of 32 is 16 times 2, which is 4 square roots of 2. And then 18 is 9 and 2. So that's 3 square roots of 2. So now 72, 32, and 18 all reduce to have square roots of 2. So now they are all like terms. So you add the 6, the 4, the 3 to get 13 square roots of 2. Subtraction is the same. You're going to subtract the outside number from the other outside number as long as the radicals are like. So 3 minus 11 is negative 8 square roots of 5. If it's not a number but a variable, then the variables have to be the same. So square root x and square root x are both the same. So again, subtract the numbers. So you get 9 square roots of x. The reason it's important to know how to add and subtract is so that we can know how to multiply. So if you have a binomial times a binomial, then we have to use FOIL. So you're going to go to your first. So you're going to multiply root 3 by root 2. So now you're back to multiplying. So 3 times 2 is 6. So you get the square root of 6. Then you're going to do the outside. So you get 3 square roots of 3. The inside. And last. So I get the square root of 6 minus 3 square roots of 3 plus 4 square roots of 2 minus 12. Are any of those like terms? No. So you're done. Okay? Same idea. We're going to FOIL. So you do first, outsides, insides, and last. You want to pay attention to when you multiply those two numbers together. So 3 times 10 became 30, but that still breaks into primes 2, 3, and 5, so you cannot simplify 30. So again, no like terms, we're done. In number 5, you have 5 times 5, which is 25. You get 5 times negative root 7, or negative 5 square roots of 7. Here you have 5 times root 7, so 5 square roots of 7. And this time, you have negative root 7 times root 7. So if you have a square root times itself, the square roots go away. Because if you actually multiplied your 7's together, you'd get the square root of 49, which we know is a perfect square, and becomes minus 7. Positive 5 square roots of 7 and negative 5 square roots of 7 are called additive inverses, because when you add them together, you get 0. So the two middle terms go away, and that square root of 49 becomes 7. So we end up with 25 minus 7, or 18. These two terms right here have a special name. Those two terms are what we call complex conjugates. So these two terms are complex conjugates of each other, meaning that you have the same first term with opposite second terms. It is also a difference of squares in terms of factoring. So you have a plus b, a minus b, which we know if we FOIL them, you get a squared minus b squared. So a squared, b squared. In order to rationalize a denominator, you have to multiply by itself if the denominator is a single term. So again, think about square root 7 times square root 7 makes the square root go away. We cannot have square roots in our denominators. Square roots in the denominators are no-nos. Kind of like dividing by 0 or having a plus or minus. So what you're going to do is you're going to multiply the top and bottom by whatever the bottom square root is. So if the bottom square root is root 3, we're going to multiply by root 3 over root 3. That's the same as multiplying by 1. So that's not changing anything about the mathematical properties of that problem. It's still worth the same because it's like multiplying by 1. Up top, you have to distribute that root 3. So you're going to end up with 5 square roots of 3 plus x square roots of 3. On the bottom, because you have root 3 times root 3, we get 3. So that is what they refer to as rationalizing the denominator. You have gotten rid of the radical from the denominator. So to rationalize the denominator, you're going to multiply by whatever is going to make the square root go away. So I've kind of hinted or said the word already today. A conjugate is something that is the opposite of the second term. So binomials of the form a square roots of b plus c square roots of d and a square roots of b minus c square roots of d are considered conjugates of each other. So again, they're a conjugate if this is positive and then is negative. That makes them conjugates. If you have a denominator with addition or subtraction, in order to rationalize the denominator, you must multiply both the top and bottom by its conjugate. So in order to rationalize a denominator with addition or subtraction, you have to multiply it by its conjugate. So you have 4 minus the square root of 2 over 4 plus the square root of 2. So we need to rationalize the denominator. So to rationalize the denominator, we're going to multiply by its conjugate. So the conjugate of the denominator is going to be 4 minus the square root of 2. And if I want to multiply by that, then I have to multiply both the top and bottom by that to be like multiplying by 1. So in order to be multiplying by 1, I have to multiply both the top and bottom by the same thing. That means I'm going to need to FOIL twice now. So I need to FOIL the top and the bottom. So 4 times 4, negative 4 square roots of 2, negative 4 square roots of 2. A negative times a negative gives a positive, and root 2 times root 2 gives 2. And then on bottom, if I wrote my complex conjugate correctly, the middle two terms should always be additive inverses of each other, meaning the two middle oi should cancel. So, and I should end up with the first squared minus the last squared. So I get 16 minus 4 square roots of 2 plus 4 square roots of 2 minus 2. And I'm super happy. It means I did this correctly because these two terms are opposites and they do cancel. The last thing I want to do is combine like terms. So 16 and 2 is 18. Negative 4 square roots of 2 and negative 4 square roots of 2 become negative 8 square roots of 2 over 16 minus 2, which is 14. Now, you could stop there, but 18, 8, and 14 are all evens. So technically, you could divide everything by 2 again and get 9 minus 4 square roots of 2 all over 7. So that's just the oversimplification or the final simplifying process. Okay. So same thing, I need to rationalize the denominator. So I'm going to multiply top and bottom by its conjugate. So I get 6 minus the square root of 2. I'm going to do that on top and bottom again, which means I need to FOIL the top and bottom. So 5 times 6 is 30, minus 6 square roots of 3, minus 5 square roots of 2, plus the square root of 6, all over 36. My middle two terms are going to cancel, minus 2. This time, because this was a 3 and this was a 2, my numerator has no like terms. My denominator, I can simply combine 36 and 2 to get 34.